Great. Thank you so much. I'm really looking forward to this discussion because it's so interdisciplinary. And I want to start with a question about given amounts of heterogeneity we see in biological networks. If we look at your brain network and my brain network, they look very different. The connectivity looks quite different, and yet clearly you can sustain many similar functions. You can communicate, homeostasis, etc. And yet, with all of this randomness we see at the cellular level and heterogeneity, for physicists, I think it's much more heterogeneity and robustness than we normally consider. So, how does robust global function, emergent functions, is still sustained from these parts? And I want to talk about one particular kind of emergent function, which is that of long time scales, which is really crucial for living systems. So, if we think about circadian cycles or memory, these are very long time scales that can persist over days or over memory lifetimes. And this definitely is much longer than the underlying time scale of the underlying chemical reactions of the cellular firing processes. So there's even a lifetime to the cells themselves that sustain these processes. And it's a very fascinating question. I think when we might be also talking about clocks today as well. So we have a day to think about these questions. And of course, how do we start to model these in a robust global way? So this is some talking about emergent phenomena. As I mentioned, clocks is fascinating, also memory and cognition. And we can also think about these processes in cells where we have very interesting dynamics, such as dynamical instability of microtubules that grow and shrink. All this emergent function is when we have many constituents that come together to produce function that's much more than the sum of each parts, as we can see from this. And while they all look very different, what I'm going to argue today is that all of these systems actually can be described by a topological model. And in particular, the dynamics can be described by the edge state of a topological phase that is going to consist of a network made out of many non-equilibrium cycles. So let me try to unpack what this means. And by discussing this idea of non-equilibrium, this is going to feature very strongly in my talk. And one reason why we think that non-equilibrium cycles are important and is going to be a key ingredient of our networks, that we actually also see a lot of non-equilibrium cycles in living systems. So, for example, these are cycles that are powered by the consumption of ATP and GTP. And this is one such example in which this is a very simple phosphorylation, dephosphorylation reaction. And it definitely, because there is a flux, this is definitely taking in energy. And it was called futile cycle because I guess the question is, well, why would there be this consumption of energy just to get back to exactly where it was? It seems futile. And yet it shows up in many different biological systems, metabolism, muscular contraction, sensory systems, etc. So why do living systems consume so much energy to do things where the purpose is not clear at all? And one might think that this could be the case that there was a lot of energy around, but generally we know that food tends to be scarce on many living systems. And so one thing that we're going to try and integrate here is that could these common motifs that appear wasteful actually contribute to this emergence of global function and robustness? So what I'm going to be discussing today is first I'm going to show in a very concrete way how we use these non-equilibrium cycles to make a topological model that can describe oscillations and clocks. Then we'll look a little bit at this question about thermodynamic efficiency. How much energy do we have to put in and how much performance do we get out? And then I want to talk about the underlying topology and some novel theory we see, because as I said, what we're seeing here is that the non-equilibrium aspect in these systems actually has very nice new properties that I'm very excited about. So I'd really love to discuss this model. So let's look at the models that we have. And so I was talking about this simple motif about phosphorylation and dephosphorylation. And this is basically the same thing, just that there's two types of phosphorylation here. So here the phosphorylations are shown. There's two types. One is this orange, and one is this pink phosphorylation, respectively, shown by the addition of this orange or pink little molecule. And the numbers of each are given by the numbers in the brackets. So this first number is the number of orange phosphorylations, and the second number is the number of pink phosphorylations. So you see here there's a pink phosphorylation and orange phosphorylation, then a pink dephosphorylation and orange dephosphorylation, so that the numbers change as we go around in the phosphorylation level. But then we can also see that for any given phosphorylation level, the system has four choices. You could phosphorylate in either the pink or orange, or dephosphorylate in the pink or the orange. And we distinguish those different choices by this four tags, where A is a pink phosphorylation, orange phosphorylation, B orange phosphorylation, etc. such that then for each phosphorylation level, we can have these 4 different tags. One can also have transitions that cycle the system between these different tags. So now we have 2 different types of transitions, these that I'm denoting in these solid transition rates and these dashed transition rates. And you can see that they also have an opposite chirality. So we can write all of this in this larger space of this phosphorylation level network, simply by repeating this motif in phosphorylation space. So this is all 2, 1, and we can start from 0, 0 on the bottom left and go up, increasing. So on the horizontal axis, it's increasing in this orange phosphorylation, and on the vertical axis, decreasing in the pink phosphorylation. So that this tiles this 2-dimensional space. And so then this motif you can see here, it's actually this motif that is just repeated along, and this motif is this one. So we have these 2 types of cycles with these different chiralities, this black or solid rates and these gray on these dash rates. And since they go in opposite chirality, when these states are roughly equal, then the system essentially forms a kind of balanced random walk, because you can see that it's going to just wander around, and it just, it's going to just cover the whole network with time. So it's going to ergodically explore the whole network as we in the steady state. So essentially a random walk across the whole network space. And this is typically what we assume to be the default state of many living systems. It's going to be diffusion, it's a random process. All the randomness is just going to lead to some non-particularly distinct steady state that just covers the whole thing. But in this network, there's actually a topological transition to a state that has very different dynamics. And that transition happens when these black rates are faster than these gray rates. And after that transition, when the black rates are faster, then the system will actually show very different dynamics once it hits the edge of the network. And you can.
Sorry, you said this, just if there's a transition from A to B and B to A back. Can it go from 1?
Oh, so can it be also reverse?
Not self-providing random.
So in the general case, yes, but there still should be some kind of chirality, and we will start to explore the case in which this chirality can be tuned all the way towards a symmetric network where there's no particular non-reciprocity. But this is a case obviously that has full reciprocity. I'm just showing this simplest case for illustration. But for the properties of this network, it does help if the cycles have some overall direction. It may not be exactly so extreme as this, but it should still have some kind of direction. Yeah, I would love to have questions during the talk, so please slow me down. And this model is going to appear again and again, so it's great to figure out to understand.
Okay, so back. So let's just take. So I just want to make sure I understand the model. So you've got these sort of internal cycles for the 2-1 state.
Yes. And
the idea that we have these internal cycles for every one of these states. Every one for example, 1, 2.
Yes.
Yeah.
The one for 1, 2 is up here.
Okay.
Exactly, and the one for 2 is yours and 2, 1, and then these 4 corners touch to give this one. So one of them here that connects between the phosphorylation levels and increases and decreases the phosphorylation.
Okay, so the other thing is the rates of phosphorylation and dephosphorylation. I guess they have different. In general, those rates are different.
You mean between this and this, or between
the red and the green arrows?
That is so. This is in general, yes, they can be different. Right now, in the simplest case, they're all the same. That's why they're all black. You can start to break that and see how it changes. Yes.
So now,
but right now there is symmetry exactly. We'll see this anyway, and it's the same. Great. So to talk about the topological transition, we can see what happens when the system hits an edge. So let's say the system is wandering around the interior, and then once it starts to hit the edge, then it's going to keep moving along the edge. And this is because you can see this by inspection. So let's say we're here, and then it can only move here. This is larger than that in the topological phase, so it's going to be more likely to go here, and then it can only go here, and this is more likely, and then this can it's only possible to go here, it's only possible to go there, and then this is more likely, and so on and so forth. So it will start to just stay around the edge. And the more it stays on the edge, the more the black is larger than the gray, the more it will stay on the edge. So this goes back to what you were saying. We can have the reverse reactions as well, but we do need some chirality in order to have a directed current. Otherwise, it will go back to the random walk once everything is balanced. So we have these two very different phases. One is simple diffusion across the whole network, is a two-dimensional dynamics, and one is an effective one-dimensional dynamics that just goes along the edge of the system. So one lower dimension, and it just keeps going around the system. And not only that this system has an idea of robustness, which is that it will just always go around the edges of the system. Oops, sorry. So here we can see that, let's say here, I already showed you that it's going to go around the edge. Let's say there are some, for whatever reason, there are some missing components or some inaccessible states. So the system, instead of just getting stuck and dissipating back into the bulk, the system here, you can see that it will just, if this is not available, then it has to turn this corner. This is more likely, it's more likely, and this is going to go here. So it's going to actually maximize the largest available phase space at all times. So it's going to always go around the edge. And so this is a notion of robustness, that this edge state is robust to inaccessible on the system. And here I just want to pause again just to see if it's model is clear.
Again, explain why it's a two-dimensional space, not say two-dimensional or something like that.
It's two-dimensional because you're saying that because we have four things. So there's two dimensions because there are two indices in which this can extend infinitely and this can also extend. So this can keep going, this can keep going up here. So that's two dimensions. And then there is also a third index, which is this little ABCD. And so, one could ask, well, isn't this a third dimension? And it is because this third index cannot vary arbitrarily. It's not something that can go ABCD, but instead each particular tag, in some sense, has a particular constraint, if you will, or particular function. So this A state always then tends to promote, a critical kind of phosphorylation. So these tags are not in this model are not independent of each other. So it's not that we could vary these numbers and the third number all at the same time. The way that this changes, so if this changes here, then this gives rise to a different set of states. Another way to think about it is, if you think about the space model lattices, this is a unit cell. Here it is light blue box, and this unit cell is then tiled along this two-dimensional lattice. And one can have different subgroups in this unit cell. So this is a 4-state unit cell. That can also be a 3-state unit cell that we also have examined that would form the carbonate lattice, set of a square lattice. So we could have different subgroups in here that are then repeated. And and then that would be then the study of different lattices to know, whether this is categorized as two-dimensional or three-dimensional. Does that answer your question?
So I guess I'm trying to see if it is possible to come up with a scheme to make it two-dimensional, but say it's because it's a cycle.
It is a cycle that it would be three-dimensional if somehow A, B, C, D could if this could cycle between A, B, C, D without changing this other index. But because it's not just 3 independent axes. In some sense, this is somehow slave to these, therefore there's one lower dimension. But I mean, I'm happy to get your intuition about how and how to understand this.
I have a really naive question. So you have these 4 internal states. How do you map your problem to the number of internal states? You can speak just briefly about that.
Are you asking for a real biological problem? Or are you saying in general?
Like in this problem, for example, how do you arrive at the internal states there?
So this is well, what we're going to see is that this model has, this model, as I showed you, has non-trivial edge states. And what we do need is some kind of non-equilibrium cycle. And to make a non-equilibrium cycle, we need at least, well, we generally we need at least 3 states or 4 states, I think. So here, this is in some sense the simplest possible version, and so we have these 4 states. And then the idea is to essentially tile a lattice and have this. So this is pretty abstract. This is sort of the minimal model that we can have. And I guess that's what we broke down. So yeah, could you maybe
So
let me
basically,
ask you-
anytime you have a cycle like
Yes.
this, whatever, Earth cycle or some other cycle in a biological cyclic process, would you always try to map it into 3 or 4 internal states? Something? How does that process work? Given some biological cyclic process.
Yeah. So I think it depends on the process. I was started by saying that we're interested in long time scales, so time scales that are not just the same time scales and underlying rates. If this time scales are really that of the underlying rates, and we know definitely oscillator models that you can have an oscillator just by having very few states. But then in that case, oscillatory time scale is the same as that of the underlying rates. So for those kinds of cycles, we really don't need this at all. It's really if we're thinking if we have a series of reactions that lead to a longer time scale, and how do we understand how that time scale emerges from that soup of networks? Then I would think about, right, can we try to maybe see some kind of pattern, because there is some regularity here, some kind of pattern in the repeated rates, and see if then that could connect somehow to these ideas. Okay.
So I guess just, you said something before about you needed at least three states.
Yes, and I know I just showed you a Intel cycle that has 2 states.
Exactly.
Yes.
Exactly. So now is the reason basically that you basically need to make some kind of 2-dimensional lattice, and basically 3 would be a triangular lattice, and that's why you need at least three states, or is there anything?
I think that's a good point. So this is definitely the futile cycle I showed was definitely out of equilibrium, because there was a flux going around. I think we can also form topological states that have just 2 states, but 2 repeated states, and at least what has been seen in the literature so far is that they normally don't have fluxes in them. I mean, you need to see current somehow we need more explicit driving in a sense, because just two systems typically they will form in the steady state will be detailed balance, and there won't be fluxes. So to see currents, which is what I want to try and do because I'm interested in non-trivial dynamics, then we do need flux. I mean, maybe there's a way to think to find fluxes in a system with just 2 in a clever way. I guess we haven't seen that yet. But this is a very interesting question. I think about what's the minimum that we need to get a flux, etc. And
Geometry or something 2D or something, or all of it 2D, because I'm thinking of trying just to make
yes.
if I want to make, I have a sense that I need, I need to at least have a triangular lattice, and so somehow that
I agree with you, because the model that I was referring to that has just 2 subunits, they formed like a quasi 1D system, like a ladder.
Yeah.
And that doesn't have fluxes, but that also has some idea of topological localization, but there are no fluxes in there. So right, in order to get a flux, we do need a 2D thing, and then one could tile, I guess, in principle, a 2-unit cell to make it 2D, but somehow we haven't seen that yet, and so maybe one could design that. But...
Okay.
Okay, so again, maybe this is connected to your next slide. So these states which are labeled by 1, 2, 3, 2, these are the number of pink and the orange labels on each of these plackets. So, and the blue squares are the maximum number that we can go to, or the blue squares?
Yes, absolutely. Yeah, you're right. You're already seeing ahead, exactly.
So then,
I mean, in this model, yes.
so then 3, 2 would be 3 of those blue becoming pink and 2 becoming orange, or that
yeah, I mean vice versa, but you have the right idea that 3 of the blue ones have orange and there's also 2 pink ones. Exactly.
So if I am thinking, like, for example, in terms of spins,
Mm-hmm.
then can you use like a conservation law that the total number of spins should be like what 6 or something more, maybe?
So
Eight
is,
maybe maximum.
so what would the spins here be? That this one is a spin and this is a spin? Or is it-
Yeah, so that's what I was thinking. I mean, like, is there a conservation on the total number of the internal states that it can go to? So maybe, so is that why you were disallowing these 3,2 states or things like that later on?
You are absolutely right that the size of the network is given by the finite size of the system, how many total orange and pink phosphorylations are allowed. In our model, because we only allow one each for each of the 6 things, you're absolutely right that it goes from 0, 0 to 6 by 6.
Okay.
Whether this could be described by spins, probably yes. But somehow I don't know if this would add a conservation. In fact,
The
because
thing is because you mentioned copy and things like that. That's what.
Yeah.
No,
yeah, so I don't know if spins will be more conserved. At least that's my intuition. But that could be an interesting part of it. Okay, great. So I'm glad that this is we are all on board with this. And so then going on to Monita's question about, well, how would we actually deal with any living systems for this? So now what idea is, as I was saying, this can give a larger time scale by putting together all of these different reactions to have this larger period. So I want to show how this could be applied to a plot. So here this is.
So before you leave that slide, we move back. So you took out sections, you brought the boundary. Well, how did you take out a section in the middle?
Then there could also be something that goes around the middle, absolutely. Yeah, so it can be an edge anywhere.
Yes.
Yes. So this could now model a long time scale, for example, the circadian rhythm of cyanobacteria. This is a very nice system because it can be isolated in the test tube. That all we need are these chi monomers and chi A and chi B, and then some ATP, and then this shows this circadian rhythm. And essentially, this is also why I drew these systems as these 6 squares, as Buddha was asking. So because chi C has 6 of these monomers that form hexamers, and each monomer has 2 sites, this S and T sites. And what happens to form the circadian rhythm is that by day, all of the T sites get phosphorylated, and then all of the S sites get phosphorylated, and then by night, all the T gets dephosphorylated, all the S gets dephosphorylated. There's also a very large space of different possible conformations and chemical reactions, as typically happens even for such a simple system. So, for example, there are these protruding loops that can be exposed, so they can be buried here that are connected to the monomers, etc. And so, just theoretically, given this very large space of possible T and S phosphorylations and conformational changes, why is there such a global and robust cycle? Why does it all go T and then S and then T goes away, S goes away? Of course, this is important for the organism to know when to reproduce, when to eat, etc., and to regulate it. But why isn't it that T and S just phosphorylates randomly? And in fact, this sort of random sort of independence reaction is often what is hypothesized. So in the literature, it is thought that individual monomers can undergo auto phosphorylation in T and S cycles. Monomers bind into hexamers, unbind into monomers. Monomers shuffle between hexamers, they can take different conformations. So monomers seem to have very much independent life of their own. So why is it that they would actually all phosphorylate together, all T and all S, in this concerted way? So we are offering a hypothesis that this could be described by a topological model. So essentially here, this is the same model as what I was describing. Now here we've added these reverse reactions for thermodynamic consistency. And as we were just discussing with Buddha, this does have an overall chirality, but we can have some reverse reactions as well, and look at how that changes. Also for the reverse state. And so now this orange and pink phosphorylations are essentially the T and the S phosphorylation sites. And these internal states could be mediated by conformational changes. So here this is describing these buried A loops, these exposed A loops as one possibility. And then chi A and chi B can play a role in mediating these internal transitions. And then this is exactly the same network as before, now with reverse reactions. And of course, as Buddha was pointing out, this now goes from 0, 0 to 6 by 6, which is the full possible phosphorylation space for 6 monomers. And we have been, looking at the literature to see whether this could be consistent with the literature. And there are some pieces of evidence. So here, the phosphorylation of the action of chi A that's promotes phosphorylation here in the S direction, and here this chi B does promote dephosphorylation, and also here chi A tends to bind to this exposed A loop. And the other ingredient that we do need also is a separation of these timescales. And there is some evidence that this phosphorylation timescale is is faster than because this is very directed, it's powered by ATP, it is faster than these sort of more diffusive reactions that are not powered by ATP. So there is a separation of timescales, and taken together, this can give rise to this kind of model to giving these in the topological phase. When the system is going on the edge, then the system will undergo all of the T sites phosphorylating, all the S sites phosphorylating, all the T sites dephosphorylating, and all the S sites dephosphorylating. And in some sense, here Momita was asking, do we have no, Mimi was telling whether how many different reactions do we have here? And so right now we actually only have two timescales here, the black and the gray. So there's a very simple model that can create this. And of course, there are other established models that also do model chi-ABC, which is for them, some of the things have been put in by hand. So for example, to get this cycle, these have to be negligible compared to that. And also this is just one phosphorylation. And so in these models, the fact that T happens and then S happens independently, something has to be put in by hand. Whereas in our case, the T and S and then T going with S goes with emerges naturally. And so there's a lot more parameters in these systems, and this is a much simpler way to describe that.
What's NWC?
That's the Monod-Riemann-Chandru model. It's a typical paradigm that motivates why the system would travel all of this way instead of hopping over. It's saying that conformational changes lock the system into place so that it has to go this way, and then the conformational changes happens as an all or nothing kind of paradigm, and then it goes down here, and then because the system is locked, then it goes back. So it's a paradigm to motivate why the system would actually do this, and it's people discuss this in biology, and this is often what is invoked as one reason why you would get a cycle. So it's I suppose one of the ideas in biology to try to account for this.
So one thing is that in this model that we have written down, a site being blue to pink does not influence the next site in some way. So for example, if there maybe changes the reaction rate in some way, that it has more propensity to become pink or orange. That kind of thing is not yet built into your model.
Absolutely. So right now we have a very sort of like this like most simplistic version, but all the rates are equal as we go along. But of course that we know in chemical reaction systems that one reaction should change the other. Yeah, so that is something that
but you can't do it simply within your model.
Yeah, we could add that into the model. Absolutely. Another thing that we also don't know, like things really change one at a time.
Yeah.
And that for that also to look at, even just looking at it on such molecular resolution is not really available. So this is really a hypothesis that gives rise to phenomenally similar dynamics, but some things can be tested, but some things like that is also difficult. Okay, great. So so this was the main model that I wanted to talk about, and then I would like to talk about some properties of the oscillator, and then I want to zoom out and just say, well, how can we think about these stochastic topological systems in general more broadly? So just to think about how good of a clock is this, and how efficient is the clock, and how well does it perform? So typically to compare the performance of clocks, we usually use the measure of coherence. And so coherence can often be described using the master equation that a lot of biochemical equations systems, including ours, are described by. Essentially, one looks at the first non-zero eigenvalue of the master equation operator. And as was brought out by, and Udo also mentioned this, that then we can compare the imaginary and real parts of that eigenvector. And there's also been very nice work in stochastic thermodynamics to try to say, well, how can we bound this? So given a certain amount of coherence that you want, the clock is very coherent in terms of very good and consistent oscillations. How much energy dissipation is required? And usually there is a bound so that one has to feed in a certain minimum amount of entry production for certain coherence that we want, which makes sense. We want it to be better, we need to drive it faster. This was again very nice work by Andre Barato recently. And here you can see what we normally expect. Every one coherence to go up, also entry production has to go up. So here, what we have in our model is you can see how these things do in our model. And here we can see that when driving it, coherence does increase as we expect. Also, this is charting the topological transition. This is increasing, it's becoming more topological in here, and also as we expect, it becomes more coherence. As we look at entropy production in here, what we see is something a little unusual, which is that here we see as we drive it, the system starts to move around more from inside. This is more from inside the interior of the system towards spending more time on the edge. And so actually entropy production, if we can break it into the bulk contribution versus the edge contribution, we see that the bulk contribution decreases with at the bottom of my slide is a bit cut off. I don't know if it's maybe it's
okay.
Maybe-
I think Zhang and
No, I think it's me.
click on it and it goes away.
Yeah, sorry,
Oh.
it was my fault.
great. Which is so we can see the bulk contribution in orange and the edge contribution in blue, and we can see that as we increase in driving, the bulk decreases, and it's because the system spends more time on the edge now, and the edge entropy production increases. But because there's many more bulk states generally in most networks compared to the edge states, the overall entropy production decreases, and so we get this interesting regime in which here we are getting less dissipation, even though the system is getting more coherence. So this is a little bit like what Pierre was discussing during the workshop, that sort of saying that we're pushing the system less, but somehow we're getting more out of it. And we can also start to compare coherence compared to other time models. This is just to look at how other clocks do. This is the NWC model again. That's a very typical one. It has a different number of states, but it has essentially the unicycle and sort of energies. And then we can also compare it to a more bilayer system that so that is more similar in a lattice form to our system. And we can just sample different parameters. So this blue is our model, this red is the MWC, and this green is the bilayer. And we can just see that that in terms of coherence, that our model does pretty well, and also it can saturate. It starts to saturate. There's different thermodynamic bounds that can be saturated, and here it starts to saturate this 28-state unicyclic model. So essentially, there's 28 states on the edge, and so it starts to approximate a unicycle on the edge when there's large driving, which is what we see and expect. So in the last part, I want to talk about just step out of clocks and just talk about the underlying topology more broadly, and also what new theory that this might enable. And this is why I'm really excited about this workshop, which is really bringing together people from different disciplines, from very theoretical to very applied. And so this is a place that I'm, very curious to discuss more. So where do some of these ideas come from? And how do we know the system is topological? So here, this is essentially studying this operator here, and especially to see whether the eigenvectors of this operator have a Barrow connection. And to see that is essentially done by integrating the eigenvectors over the Fourier domain. The reason why there's a Fourier domain is because, as you saw, our systems have this lattice, this lattice pattern. This lattice pattern then allows us to write a system in Fourier, explore the system in Fourier space, and then this is a periodic domain, and we can see how the same eigenvector winds around this periodic domain. Essentially, if it winds, the system is topological. If it doesn't wind, the system is trivial. And the winding of this in this Fourier space, or in this periodic space, essentially tells us about what happens, or whether or not we will get edge states by about boundary correspondence. And these are ideas that were developed for quantum systems. And the reason why we can invoke these ideas is because we can see that the Schrödinger equation is very similar to the master equation up to a constant. And so if we can map it over, the eigenvectors essentially stay the same if we have an effective Schrödinger equation. And since the eigenvectors is where we see now there is a winding or not a winding, then we can use some of these ideas because these ideas were developed for the eigenvectors of the Schrödinger equation.
So how is this the finite size of the lattice? Because in many of these, one of you thinking these systems are in very large lattices and then of course when something happens on the edge, it's very different from happening in the bulk because the edge has much lower dimension, much lower size. But if you've got your small lattice, then the difference
Then
between
the
the edge
edge-
and the boundaries
absolutely.
becomes kind of, it's not such a big difference.
Absolutely.
So what will, because that means that I imagine, I'm thinking that there's going to be some typical, like some coherent boundary region.
Absolutely.
And you've got to compare that with roughly how large that is compared to the system size.
Absolutely.
So this becomes useful presumably when when this ratio is small, when the boundary is much smaller than the system size. So that's presumably experimentally testable, but you could then look for things which are more complicated.
Absolutely.
Then the corresponds, because that would be, let's say you didn't have 6, but you had 12 or something, then this would be more efficient. I mean, in the sense that you would have been more robust in some sense, because if you compare the ones which are very around the edges to the ones which probably, let's say, ones we're going to move above. So can you?
Absolutely,
can you say
and
something about
I think as you said, you said that very clearly, that it depends on the sort of consumer length scale. How much do the edge states feed back into the bulk, and you have to compare that with the system size. If the system size is much larger, then that's a good separation of scales. If actually the consumer length is quite small, then it's going to be fine even with the small system size. And this, how this decay length depends on system parameters. But the other thing that's also very interesting is how this decays. And if this decays exponentially, usually it's a lot more robust than if it decays as a power law. So I'm actually going to discuss this, but this is a great point. This is a very interesting point to discuss how this relation of the edges and the boundary. But that's the quick summary of what I was going to show a little bit. So so just to say that, yeah, let's look phenomenologically at how this works in principle, in practice with a finite system. You can see that when we simulate it, the system goes around the boundaries. This is a more slowed down version. So it's a 2-dimensional plane, time in the vertical axis. We see that it forms a random walk, and then once it hits the edge, it goes around, so that in a steady state limit, it stays on the edge. But to go back to Tenny's point specifically, let's examine the nature of the edge states so that we know how robust they are. In this system where everything is directed and there is no reverse reaction, so not the case that Will was asking about, then it's that the edge states are exponentially localized and they stay very nice on the edge, even in small systems, it's not going to be into each other because you can see that they're still quite well separated. But once we start to perturb this, so start to move towards to a more reciprocal system, then this is not going to be, then firstly this computer length scale is going to get larger. We can start moving away from exponential more into other things that are so then the separation becomes a lot less good. So yeah, that's a really great question, and I think that is a very important question for the study and to apply this to real systems and to think about how do these properties affect each other. So that's a great point.
How does the boundary spectrum of convex?
That's a great question. And well, firstly, we already saw that in this coherence. Let me know if you want me to show it. In this coherence measure of how well does it perform as an oscillator, it was the ratio of the imaginary components over the real components. So in some sense, it suggests that this imaginary component is crucial, because if that's 0, then the coherence is 0. That's not.
I guess I'm trying to think in the computation, you focus on the, well, I'd say, obviously, it's many ground state building it up, and it's very statistic like this. But how do you say you had steady state?
That's a great question, and that was something that I was going to show exactly. And this is different because in master equations we want to consider the steady state, and in quantum systems we want to consider the zero energy state, and these are not the same state, and this will lead to some differences. And also this question about the imaginary spectrum is very important. I was going to talk about it. That is the new work that I wanted to show. And I love it that we just had a talk sort of discussing between quantum and classical correspondence, and this is essentially in the similar spirit. So great. So this was exactly what I was going to show next, which is to start to think about what is the nature of non-equilibrium in these systems, because non-equilibrium systems is the only reason why we have an imaginary spectrum. Essentially because if we start to think about these master equilibrium systems, and if we have non-reciprocal transitions, W is non-symmetric. And of course, we know in living systems, these non-reciprocal interactions happen everywhere. But also, this has to be non-symmetric in order to have an imaginary spectrum, which we do know is important, at least for oscillations. But what about more generally? And so what we do see is that this gives rise to new properties in these stochastic systems for several reasons. And I'm just going to spend the last few minutes just talking about this very quickly. So Essentially, if we want to map between quantum and classical, so what you think of this A is really the Hamiltonian. I will change my notation in the next round. But the difference between the operators, between the master equation operator and actually the quantum operator, what I had said before that they can be mapped, it's only true actually when the system is periodic. And that is because the operators differ by a diagonal term. Essentially, the master equation has this additional diagonal term that enforces probability conservation. When the system is periodic, then this diagonal term is just proportional to the identity. And so then the spectra are the same and it's just shifted up and down. Please stop me if I'm going too fast, but I know that this is the end. So, and what happens is that when the system is not periodic, when there are boundaries, as Tanny was pointing out, then the spectra are quite different because then generically D will change the spectra. So we can see this, when just comparing the quantum and the stochastic versions, just looking at a very simple 1D chain. And here 1D reciprocal chain or Hermitian chain. So the system is only real. Already we see that the spectra are largely similar, but there's a few things. Firstly, the spectra is shifted, and that's a shift due to this overall shift that we expect, but also the open boundaries makes it so that there is some additional there's an additional state here in the quantum system, for example. And this goes back to what was just pointed out, that the states of interest are also different for stochastic and quantum systems. So in quantum systems, generally, we do care about the Fermi energy, so that's at 0. And in stochastic systems, we generally care about the steady state of the system. So that's highlighted in green in both cases. And even though the spectra are sort of just shifting over, and what is interesting here is that now what we see is that this correspondence between the bulk and the boundary that is such a cornerstone of quantum topological systems is now different in stochastic systems. So we had established that these have the same operator and hence the same topological invariant. We can map everything over only when they're periodic, or in some sense in the bulk. And with open boundaries, then this longest lived states look different. The longest living states being a steady state versus the zero energy state. Typically, in quantum systems, there has been this correspondence between the bulk invariant and this zero energy state. This is the bulk boundary correspondence that is known and loved. So here you see that this zero mode has this beautiful edge state, and this is the same network for both of them. But yet this steady state here in this stochastic system, you can see it's homogeneous. And so even though they have the same bulk, you can see that the boundary states look very different. And so here, the reciprocal state stochastic systems do not have edge states, even when the quantum one does. And this is what you were saying, I think. It's a couple of things. The state of interest is different, and the other, and also the spectrum is different. And so then to just look at what happens when we add non-reciprocity. So this is a pretty important ingredient here. You can see after all. So everything now is more biased towards the right. And then we do see that now for the same network, if we look at this zero energy state and the steady state, we do see that things do pile up in a way that looks much more similar. So stochastic systems do require non-reciprocity with edge states, unlike stochastic systems. So we are writing this up and we are hoping to put it on the archive, and then also we are looking at other interesting things exactly like what you were asking. So then why do stochastic systems require non-reciprocity? The imaginary spectrum is definitely a big part of it. So we are exploring these things, and of course they do behave differently from quantum systems, and so we're exploring, and I would be very happy to chat more if you have intuition and thoughts about this. But I think I should close now. This is just to very crucial what Meron was asking. Can we have a different kind of motif? So if we have a 3-state motif here, we form a conglomerate lattice. Sorry, let me just show that again. We can form a conglomerate lattice, so there's a triangle like what Tanny was saying, and we can see that it also has edge states. And so I just want to summarize that here we have this topological framework with different dynamics. We can study clocks in there, and we see some efficient edge localization, small precision with simultaneously less cost, and there's also new theoretical properties for these stochastic systems in general. And I really want to thank my group. So Chongbin, my student, did the work on these clocks. Alexandra, my postdoc, did work on some of these stochastic quantum properties. And thank you all for your questions.
Thank you very much. Are there any questions? Comment?
Yeah, so I guess I comment which is related to, it seems that one of the attractive things about it, way of looking at things is that things which are built by hand in many of these models essentially seem to emerge naturally by putting in these ingredients essentially. And it seems to me that a big ingredient in this is this non-reciprocal breaking digital balance. Essentially, it gives you things which look like, I guess, cycles or Hamiltonian-like dynamics in these systems which you wouldn't get if you had digital balance, when you just get relaxation to the ground state. So, I mean, did you ever like try to study, let's say, which and whether or not the transition to sequence behavior does it happen as soon as you make it non-reciprocal, or does it happen at some finite value of breaking these if you want similar between the arrows? Because essentially what you've done is you've got different arrows. So you see something about that. But how does this difference between the arrows affect all what you observe?
Yeah. So typically what we're seeing in these stochastic systems is that things often ramp up more gradually than in quantum systems. Quantum systems, you often get, very nice, sometimes cleaner properties like, like boom versus nothing. That quantize. And then in these stochastic systems, they ramp up more slowly. So if we were to break it a little bit, then we get a little bit, but so it does ramp up slowly. And so in stochastic systems, there's often also more hybridization that we see between different states, probably because of this diagonal reflecting term. So this is also why stochastic a lot of things require they need more stronger conditions to show these stochastic. So quantum systems in the Hermitian limit, in this reciprocal limit, they can already have that state. Stochastic systems can't. And so stochastic systems require stronger conditions, if you will, in order to show these things. So just to say that to respond to your question, things happen, things you have the months to break it, but they will wrap up. So if you want to see clear signatures, you probably have to repeat them all.
So I mean, is that something like H bar? So can you make a mapping of the thing that into H bar? So that maybe with your, because essentially, there's something that has to be small in order or large, and in order for these effects to be strong. So
yeah, that's a great question. And I mean, I would say that in some sense, if you think about what also drives these cycles, there are units of ATP. I mean, in biology as well, it's not that you can, put an ATP in a continuous manner. So things come in packets there as well. All this is so new. Again, these are also active systems, right? It's sort of driven by this internal energy source. And also in quantum systems, often we don't really have regular systems. A lot of times quantum systems are driven by some external magnetic flux, or there can be some internal hawking as well, but I'm not sure how long. I don't know how well things are quantized in that regime either. So there's a lot here to explore. A lot of good ideas. I do think that, hopefully we can start to think about how this quantization of these chemical packets can lead to a different kind of unit, but that's all, waiting to be explored.
In one of the main logistics, there's a lot of excitement about the time breakpoint. Somehow it seems similar to these blocks. But I guess one of the correct that all these being period is kind of increasing the systems.
Yes.
I guess those kinds of systems.
Yeah, these sections so they're actually being driven in a periodic fashion. But it is interesting, but I guess the
discrete effects.
what is it?
Yeah, it's discrete time crystal, but it's driven at one period and then you get a period of time. The original suggestion was that you put it in continuous time, and then that was somehow that happened. But the street time, they're driven during the models, they use that right.
Yeah, I mean, I'm curious. So, how do you think that period doubling comes into?
Well, that's what they call it, street time. I guess you could
Yeah, I mean, this is something that would be great to explore, and what makes me seeing in time crystals that what a system that's originally not, doesn't look topological, that, you know, with driving, you get new phases, and also, and there's all this research now also showing that you can get things without having to use the usual, you know, quantum effects of having imaginary terms, that you can get some things in pencils. And so I think also in these systems as well, it could be interesting to see whether some of those new descriptions, that don't use imaginary terms could use those, like, yeah.
Any other question? Comment? If not, let's start with Steve, I think.